Okay, so this will be chapter 3 in your textbook. And it's called Roots and Powers. Basically, what's going to happen in this section is a lot of work just with numbers. Okay, that's all we're going to be really working on, numbers. If you take a look at the big ideas, square roots and cube roots, and some exponent laws. Okay? You can put that here. Exponent laws. Okay? There is other desks if you want to sit in another desk. There's one there. There's two at the tables. Maybe you want to go right there. All right. We jump in here. Prime factorization. All right. So, in mathematics, there's a fundamental rule. Well, not really a rule, it's just a fundamental law. It just happens no matter what. Is that every composite number, you can jot this down. Every composite number can be expressed as a product of primes. Okay, this is a fundamental idea about numbers. And the way you can think about it is you can relate it to science. In science, what would this be referred to? H2O is water, sure. It is a compound, do you agree? All right. It is a compound. What is it made up of? 2 hydrogens and 1 oxygen. These are the elements. Now you can think of this similar in math. Let's say we have the number 10. Is number 10 prime or composite? First of all, what's a prime? What's a prime? Any number that is divisible by what? 1 and itself only. Is 10 only divisible by 10? It could also be divided by 2 and the result would be 5. So we could express 10 as 2 times 5. Do you agree? All right, I'll switch colors. These 2 and 5, are they composite or prime? 2 and 5. What can 2 be divided by? 2 only, right? And itself, or pardon me, 2 and 1 only. 5 can only be divided by 5 and 1 only. So these are the primes. This is the composite. So just think of it the way you'd think of H2O as being the compound made up of the elements. You can't get any lower than the elements on the periodic table. Just like you can't get any lower than primes when you break down composite numbers. So 10 is like the compound, the 2 and the 5 are like the elements. Do you guys feel okay about that? Okay, and then this is just a math sort of agreement that was made. 1 is not considered prime. You don't have to care about that. It's just for like university scholars and the way that they write their books. 1 is not considered prime. So could we just generally think of the first few primes so that everybody has a good chance at this. Let's generate the list of the first few primes. And these go on for forever. There's an infinite amount of primes, but we'll just do the first few. So it starts with 2. Before we jump to the next one, 2 is very special because 2 is the only even prime. Okay? After 2, it's 3, 5. Good. Everyone says 9 for some reason. 9's divided by 3, right? Keep going after 9 is good. Keep going. Good. 17, good. 19, good. 23, 24, 25, 26, 27, 28, 29. Okay, so that list goes on forever. You could keep finding more and more and more. And it was actually proved long time ago that there's an infinite amount of primes, but that's just the first few to get us going. What we're interested in is this prime factorization. If I could just select the highlighter. That's what we're interested in right here. Prime factorization. What does it mean to factorize? These prime numbers that I've circled over here, those are also the what of 10? These are the factors of 10. Do you agree? There's more factors of 10. 1 and 10 are also factors of 10, but we're interested in prime factorization. We're interested in prime factors. So find the prime factors of 3300. That's our goal here. So you can do a factor tree, you can do a factor table, lots that you can do. I'm just going to do a factor table. So I'm just going to do like sort of some upside down 3300. You might have done some of this stuff in elementary school with like division. You draw different ways of, they're just tables. So like all I'm interested in is finding prime factors. And then later when we're doing more interesting stuff, we'll see why this helps us. And hopefully on the test you don't have big numbers like this. You might, but anyways, divide out a prime number. What's the first prime number you should try? Yeah, it's the first one on the list, right? I would just try these numbers on our list, and maybe on the day of your test, before you start your exam, you just write those out so you have them in front of you. Anyways, I'll try 2. Why does 2 work no matter what for this number? Good, because it's even. If it's an even number, try 2. So that's a tip. If it's even, use 2. That's just a tip. Okay, divide 3300 by 2. I need a calculator. I suck at this. Yeah, I'll just use my calculator. 3300 divided by 2. I got 1650. Still even? It's still even? Use 2 again. 825. No longer even. No longer even. So now I need to go to the next number on the list. Does 825 divide by 3? Does it? How do I know? When I do the division, I don't want any decimals. We have to divide perfectly. So it does divide by 3. 825 divided by 3 is 275. Keep trying 3. See if it works again. It does not work. What's the next number on the list? Does it divide by 5? Without even checking, how do you know it divides by 5? Because it ends in a 5 or a 0. So let's try 5 and see what we get. 55? And 55, oh, come on, board. 55, I know that one. What's the times table that gets you to 55? 5 times 11, right? So I'll finish off with 5, and then I'm left with 11. 11 is prime. Do you agree? So I'm done. Okay? But I'll just pull out that 11 one more time just to get the 1. And now I'm done. I have all the, yeah, keep passing it around. I'll take it. So those are the prime factors. Okay, did I miss anybody? Roxanne is absent. Nika is absent. Tyler? Tyler, absent. Ben. Hudson is absent. Whatever. Keep going. Anyways, let's write all this out. 3, 3, 0, 0 is equal to 2 times 2 times 3 times 5 times 11. Do you guys agree with that statement? 2 5s, thank you very much. Sneak that in there. Do you guys agree with that? Yeah, and he said times 1 if you really wanted to, but that's kind of why those mathematicians in the universities decided that, they decided that 1 is not going to be considered prime. That's kind of why they decided that. So you don't always have to include 1. Anywho-ha, let's keep going. This thing here, is that nice to write it like that, or is that really annoying? It's kind of long. So what symbols do we use to represent repeated multiplication? Exponents. We have how many factors of 2? 2. We have how many factors of 3? Notice I don't write the 1. How many factors of 5? And how many factors of 11? Okay? You guys feel okay about that? It might seem like at this point, like, why am I doing this? Later we'll see how it helps. Okay, you guys can try the next one. 2, 6, 4, 6. All right, so 2, 6, 4, 6. Did you divide it by 2 at first? And what did you get? 1323. So I'm doing a tree diagram, and I'm just going to show you how difficult the tree diagram can be. You sort of run out of space. 1323, that is not going to divide by 2. Does it divide by 3? Yes, it does. And then 441 can keep going. Divide that by 3. Oh, it works again. So you see I've run out of room? I don't know. It just takes up a lot of space, the tree diagram. So does 147 by 3 again, right? Oops, not 149, just 49. And then 49 is 7 and 7, right? So 2, 6, 4, 6. How many factors of 2? How many factors of 3? How many factors of 7? Okay, so this is what you want. Whether you do the table or the tree, that's what I want. Two times 3 times 3 times 3 times 7 times 7. 2, 6, 4, 6. Okay, I did it right. Yay. I will not mark you on your method. Okay? If you get this thing in the box, you're good to go. As long as you show your work. Is that fair? I think most people prefer the tables, in my experience. The tree just gets everywhere. Yeah. Okay, let's keep going. Let's keep rolling. GCF. Greatest common factor. What is the greatest common factor? Okay, let's go. GCF. Greatest common factor. the number, actually let's go the largest number that is common. I'm sorry you guys, I gotta change this. The largest factor or else it just doesn't work. The largest factor that is common, I mean that's exact, I'm just defining the acronym. G, what's G stand for? Greatest or largest? Factor, what's a factor? Something that multiplies to another number? That's common. Okay, so what does it mean? Common. You'll have like a set of numbers. Like look at the example. 138 and 198. What's the biggest number that divides those two? What's the biggest factor of those two? Okay, well let's try it out. If I was to do a couple tree diagrams and then analyze it, I'd have all this work done and it would be kind of nasty and I'd look at it. I'm going to use the table and I'm going to put both in there with a comma. And if I can find a common factor for both, then I'm laughing. So, do both of those values divide by 2? And again, I'm pulling out primes. So factor, common, primes. Only. That's sort of why we did the previous page. So divide out 2 out of both. What do you get? 69 and 99. Now those two values won't divide by 2, will they? What's the next number on the list? See if that works. See if 3 works. Here I got 23 and then 33. Now, can I keep going on this? Someone said no. Why? Why can't you keep going? 23 is prime. Yeah. 23 is prime. You're done. Nothing left to factor. Okay, so let me just ask you guys, it's just a couple straight up questions. Is 2 a common factor? Is 3 a common factor? Yeah, so but what's the greatest common factor? 6. If 2 divides it, and if 3 divides it, then 6 also divides it, because that's the product of all these. Okay? So the product of all common prime factors will be the GCF. The product of all common prime factors is the GCF. So for us, 2 times 3 is 6. And I'll just give you the nerdy like math, computer science way of writing this. GCF 138, 198 equals 6. Okay? That's sort of the nerdy way of writing it. If you just put 6 on your test and you had all your work, I would definitely give you that mark. This is just like a kind of a nerdy way to do it. And I like it, because I'm a nerd. Try the next one. This one's on you. You guys can try my process. Okay? And for you guys, if you want, you can go ahead, you can highlight those side values to try to remind you that you need to multiply them. Okay. So you guys can try the next one. Do it by yourself. All right. Let's get the answer up for this one. Greatest common factor for 90 and 25. 225. First, you started with which value? 2 doesn't work because the 225, right? So you started with 3 and 3 worked? First one I can do in my head, the second one I can't, so I use my calculator. That's 75. Does 3 work for these ones? Yes, it does. Even though I knew 5 worked, I'm just going to check to see if 3 works. That way I'm being systematic. Then I get 10 and 25. Now I'll go to the 5, and I'll get 2 and 5. So then your GCF will be the product of these guys on the side. 3 times 3 times 5. 45. And you can just check. Like, does 90 divide by 45? Yes. Does 225 divide by 45? Yes. All right. So we got some momentum. We'll skip the lowest common multiple for now that you have some momentum going. And I want you to try these first 2 examples on the next page after. We'll go back to the LCM. Okay, so if you've already done this, that's great. I'm just going to quickly put up these answers so you can just double check your work with mine. All right, so there's the first one. You guys okay with that? I'll say one thing. I noticed one student got to here and then stopped. Make sure that you get to the 1 at the end. Okay, make sure that you get to the 1 at the end. You times them at the end. Okay, 180 divides by 2. Divides by 2 again. Divides by 3. Divides by 3 again. Divides by 5. There's that one. 2 squared times 3 squared times 5. Sorry? Well, then you've messed up. There's only one weighted. There's only one final weight because it's the same. Because the order of multiplication does not matter. 2 times 5 is the same as 5 times 2, right? Order of multiplication doesn't matter. So 2646, that one's already in the notes, so let's quickly just do 6300. Any questions about that last one? Okay, how about that GCF then? Divide by 2, I get 12 and 30. Divide by 2, I get 6 and 15. Divide by 3, I get 2 and 5. Now I'm done. The GCF is these guys, right? 2 times 2 times 3, 12. That means 24 can divide by 12 and 60 can divide by 12. And nothing larger than 12 will divide both of those. Divide by 2, help me out. 63 and 72. Does 3 work? What do you get? 21 and 24. 3 works again, yeah? Okay, and then 7 and 8. There's nothing that both divides 7 and 8, right? So you're done. That's the answer. 2 times 3 squared. 2 times 9 is 18. Okay, and I'll just leave those last two, unless you want them. I'll just put the answers. You can do them yourself. Make sure you can prove that it's 12 and 5. So even though you know the answer, it's not done for you. Just show that you can do it as well. All right, so the least common multiple, that's the last one we have to do today. And it's not as nice as the other ones, that's for sure. The actual definition, like in math language, is very complex. But I will try my hardest to give it to you. And again, just the acronym LCM, it defines itself. It's the least common multiple between a set of numbers. Okay, I'll just tell you that it's used for adding fractions. You might remember that. Can we do just a quick demonstration of adding fractions? Like, what's a half plus a third? I bet a lot of you hated this in junior high. Like, so many people want to put 2 over 5, right? You got to find the common denominator. So, and then someone just said 6 right away, because they probably times 2 and 3 to get 6. So then this would be, what's a half when you're out of 6? Good. And what's a third when you're out of 6? 2. So now you have 3/6 plus 2/6 altogether for 5/6. So a lot of people in our society hate using fractions. They hate it. They literally, it's the bane of their existence. And I'm not sure why, because I'm a math brain and it's easy for me, but some people really hate it. That's just the way it is. But I'll just tell you that's where it's used for. Also, like, let's say you had like this. 1/2 x equals 1/3 plus 2. If that was your equation, this is like, oh my gosh, I cannot solve this equation. But if I use the LCM in a clever way, let's just times this side of the equation by 6 and times this side of the equation by 6. Then the equation becomes way less challenging. If you times by 6 on one side and times by 6 on the other side, that's okay, right? Do one thing to one side, do the other. And then you get on this side 3x. The 6 comes in. 6 divided by 3 is 2, and 6 times 2 is 12. I think that's a lot easier to deal with than that first thing, right? So we can use LCM in a variety of ways in the math class. Okay? And again, it's pretty much defined by the acronym. It's the lowest common multiple. So for like 2 and 3, we know it's 6. You could do a list of all the multiples. Watch this, all the multiples. 2, 4, 6, 8, 10, and so on. Do the multiples for 3. 3, 6, 9, 12, and so on. And the first one that matches is the least common multiple. Because multiples is like skip counting, right? What's the multiples of 5? 5, 10, 15, 20, 25. What's the factors of 5? 5 and 1. So don't get those two confused. Don't screw up factor with multiple and get them mixed up. Okay? Now, determining the least common multiple for 18, 20, and 30, you can do that. You can be like 18, 36, and you could generate this list just using my calculator, just repeatedly adding 18, 54, 72, 90, 108. But how do you know when to stop? You don't. Try the next one, 20. This one's easier. 20, 40, 60, 80, 100, 120. How do I know when to stop? You just don't. This one's easier. 30, 60, 90, 120, 150, 180. Did I get any that match yet? Oh, I see a 120. Does the first one get to 120? Add 18 to that. Oh, so this method doesn't seem very good. How do you know when to stop? And I know when to stop because I know the answer. Because I'm the teacher and I looked this up. So you see how I found it? Was that the best process? It wasn't great, was it? It took time. It will eventually work. It's not very effective, especially for large numbers. Especially if you had like, what if you had like 6 or 7 numbers in your list? Like I only have 3 numbers to deal with, 18, 20, and 30. What if I had like 10? Make 10 lists? Oh, that would be awful. But doable, yeah, but doable. Okay. So I'll show you the way to do it with prime factors. Okay. Break down 18. Divides by 2, you get 9. Divide by 3, you get 3. Take out the 3, you get 1. So that one's done. 2 times 3 squared. All right, do the next one. Do 20. Divide by 2, you get 10. Divide by 2, you get 5. Divide by 5, you get 1. That one's done. 2 squared times 5. And the last one is 30. Divide by 2, you get 15. Divide by 3, you get 5. Divide by 5, you get 1. That one's 2 times 3 times 5. Okay. And now here's the magic. The LCM of 2 numbers. Let's just say in general. If we were just doing 2 numbers, it would be a prime to the max power. That's prime 1. Prime 2 to the max power times prime 3 to the max, and so on. That's some simplified math jargon that I can't really give to you in a deep way. But if we look at what we have, what are all the P1, P2, and P3 available to us? What are the primes that are available to us? 2, 3, and 5. So for the LCM of 18, 20, and 30, it's all the common primes. Whoops. It's all the common primes to the maximum power. So what's the maximum power for 2? Yeah, it's 2. What's the maximum power for the 3? 2. And what's the maximum power for the 5? 1. So that's it. $180. So this one is by far the hardest one to remember. I think the prime factorization, the first page, could you guys do that without any studying? Probably, right? The GCF, could you do that one without studying? You just times the numbers on the side? Probably. Could you do this one without studying? Probably not. Okay, so let's do another one together. 28, 42, oops, let's do them separately, my bad. 28, 42, and 63. Okay, so I'll let you factor them separately, and then I'll help you out with the final answer. Okay, let's rip through these quickly. How did 28 go? 227, lovely. 42, 21, and then 3, and then 7. 3 goes right to 21, and then 3 to 7, and then 7. Now you could just scan. What are the primes that we have available to us? 2, 3, and 7, right? So just jot those down. 2, 3, and 7. Now you just have to put the maximum power that occurs for each one. For the first one, what do you get? 2 squared times 7. And the second one is just 2 times 3 times 7. And the last one is just 3 squared times 7. So what's the maximum that occurs for the 2? The squared, right? So put a 2 there. What's the maximum that occurs for the 3? 2, right? And the maximum for 7 is 1. So you don't have to write the 1, but there it is. 252. All right. There it is. Now you can try the next page. You can try the bottom. And no homework tonight. I'm giving you a break. Tomorrow, we'll finish the last 2 word problems, and then I'll give you the block to finish the homework in class. Sound fair? Let's go pause this video, guys.